Hello, welcome to Module 2 of the course on pericyclic reactions and organic photochemistry. In this particular module, we will talk about the molecular orbitals of polyene system and their symmetry properties. Then we will also consider the various methods of analyzing the pericyclic reactions. Now let us first define what are pericyclic reactions. Pericyclic reactions are concerted reactions that proceed via a cyclic transition state. The cyclic transition state is a must, otherwise it could be a concerted reaction but not a pericyclic reaction. There are no distinct intermediates formed in these reactions. That means they are concerted, they are starting material, transition state, and it goes through a product. The bond forming and bond breaking steps are simultaneous, but they are not necessarily synchronous. Now the word simultaneous as well as synchronous essentially means the timing of the events. Simultaneous means it occurs at the same time, but synchronous precisely tells to what extent it is happening. In other words, the extent to which a bond forming step and the bond breaking steps need not be equal in a pericyclic reaction. They could occur at different extent at a given time. So pericyclic reactions are essentially reactions proceeding through a cyclic transition state without the formation of any kind of an intermediate, in the sense that the bond forming as well as the bond breaking steps are taking place simultaneously but not necessarily synchronously. So this is a broad definition of any pericyclic reaction. From the potential energy point of view, one can define the pericyclic reaction as the one going from the reactant side to the product side through a cyclic transition state. And you see here it's written negative delta S double dagger. In other words, the entropy change in a pericyclic reaction is always negative, or the entropy of activation is always negative because of a very organized cyclic transition state that through which the reactions proceed. So therefore it causes some amount of entropy factor, entropy of activation being negative for a highly organized system like a cyclic transition state in this particular instance. So there is some significance associated with the negative delta S double dagger and the pericyclic reaction transition state being very organized. Now pericyclic reactions can be very broadly classified into 5 different categories. These are called electrocyclic reactions. They could be a ring closing reaction or ring opening reaction, depending upon whether ring is formed or a compound which has a cyclic structure undergoes the opening of the ring reaction. Second class of reactions are the cycloaddition reaction. Cycloaddition reactions are reactions where two components add to form a cyclic compound. The reverse of that process would be the cycloreversion process. Diels-Alder reaction is a good example of a cycloaddition reaction. The retro-Diels-Alder reaction would be a cycloreversion reaction. Then comes the sigmatropic rearrangement, where a sigma bond is broken and then subsequently the molecular rearrangement takes place during the course of the pericyclic step. The fourth kind of pericyclic reactions are the chelotropic reactions. Here small molecules like carbon monoxide, carbon dioxide, nitrogen and so on are eliminated during the course of the pericyclic reaction. And finally comes the group transfer reaction. These are reactions where, for example, a pair of hydrogen atoms are transferred in a pericyclic manner or in a concerted manner to undergo hydrogenation reaction. We'll see some examples of the group transfer reaction towards the end of the session. We'll start with the methods of analyzing pericyclic reaction. Now the pericyclic reaction, as we define, it is a reaction which proceeds through a cyclic transition state without the involvement of any kind of an intermediate stage. So there was a time that scientists thought that the pericyclic reactions are no mechanism reactions, but on the contrary, over a period of the last 30-40 years, the theoretical development as well as the practical aspects of pericyclic reactions have given a wealth of information regarding the mechanism of pericyclic reactions. Now pericyclic reactions have very strong foundation in theoretical organic chemistry, in quantum mechanics. Now these are the various methods by which the pericyclic reactions can be analyzed. The first methodology is called the orbital symmetry correlation methodology, largely developed by Hoffman, Langwitt-Higgins and Abramson. In this particular methodology, the symmetry properties of the starting molecular orbitals are correlated to the symmetry properties of the product molecular orbital. We'll see more details of how this methodology works as we proceed with the modules. The second methodology is called the frontier molecular orbital methodology. In the frontier molecular orbital methodology, we consider interaction between frontier molecular orbitals. What are frontier molecular orbitals? You have a set of occupied molecular orbital and unoccupied antibonding molecular orbital in any molecular orbital picture of a molecule. Now, the highest occupied molecular orbital and the lowest unoccupied molecular orbital, which could be an antibonding molecular orbital, are called the frontier molecular orbitals. So this interaction between, let us say, compound A and B, the interaction between the HOMO of highest occupied molecular orbital, which is abbreviated as HOMO, H-O-M-O, is the interaction between this particular molecular orbital and the lowest unoccupied molecular orbital, L-U-M-O, LUMO. This interaction is what is being considered in the frontier molecular orbital picture. This is largely developed by Hoffman and Fukuai. Fukuai is a Japanese scientist. Hoffman is an American scientist. They are largely responsible for the development of this particular theory. Then comes the transition state aromaticity method. Because all pericyclic reactions go through a cyclic transition state, depending upon how many electrons are involved and how the electrons are being overlapping with respect to each other, one can define the transition state as an aromatic transition state or an anti-aromatic transition state. And based on this transition state aromaticity, one can predict or one can propose a mechanism for the pericyclic reaction. This is largely developed by M.J.S. Dewar and Zimmermann. Now, the Woodward-Hoffmann rules are essentially the rules that are derived by applying any one of this methodology to predict the allowedness or the disallowedness of pericyclic reaction under the conditions of thermal excitation or photochemical excitation, as the case may be. So Woodward-Hoffmann rule essentially not only governs, it predicts the possibility of a pericyclic reaction taking place either under thermal condition or photochemical condition. It can also very precisely predict whether the reaction is allowed or disallowed under the reaction condition. So in order to understand the Woodward-Hoffmann rule, which are derived from the methods of analyzing the pericyclic reaction by these three methodologies, it is necessary to have a very good understanding of the molecular orbital pictures of conjugated polyene system and also identify the symmetry property with respect to certain symmetry elements. And this is essential in order to apply these methods or in order to understand these methods and their application in the analysis of pericyclic reaction. So let us have a look at one by one. Before that, let us see the scientists who are behind the development of this theory. R.B. Woodward is was a professor at Harvard University, and he is largely responsible for the synthesis part of the pericyclic reaction. In other words, using pericyclic reaction, he synthesized a lot of molecules. In the process, he also showed the allowedness and disallowedness experimentally for many of the pericyclic reaction. Hoffman is from the Cornell University. He is a theoretical chemist, and he is responsible for the development of the frontier molecular orbital theory and many other theories related to the pericyclic reaction. Longwit Higgins is the person who is involved in the development of the orbital correlation method, symmetry correlation method. M.J.S. Dewar and Zimmermann are responsible for the development of the transition state aromaticity model. Finally, Fukuai, in combination with Professor Hoffman, were responsible for the development of the frontier molecular orbital methodology. Now, how does one construct a molecular orbital picture of a polyene system? This is what I am trying to explain in the next few slides. Now, although there are sigma framework and CH bonds being present in every organic molecule, it is a pi framework that are important in the pericyclic reaction. So the construction of the pi molecular orbital can be taken independent of the sigma or the sigma bonds, namely the C sigma bond and the CH sigma bonds. Although there may be hybridization changes during the course of the pericyclic reaction, the molecular orbital levels of the sigma framework are relatively unaffected. So one can independently treat the pi molecular orbital just like you would do by Huckel molecular orbital theory, for example. without bothering much about the carbon-carbon sigma bonds or the carbon-hydrogen sigma bonds which may be present in the molecular system. Now for a conjugated polyene system, let us take butadiene. There are two double bonds in butadiene. That means there are 4 pi molecular orbitals. So if there are 4 pi molecular orbitals, then there must be 4 electrons, 4 pi electrons should be occupied in 4 pi molecular orbital, out of which half of it will be bonding molecular orbital. So 4 by 2 will be 2. So 2 bonding molecular orbitals and 2 antibonding molecular orbitals will be present. If you take hexatriene, 135 hexatriene, there are 6 pi electrons. That means there should be 6 molecular orbitals. The 6 pi electrons are occupied in 3 bonding molecular orbitals, 2 each of the bonding molecular orbital, and 3 antibonding molecular orbital, which are empty or antibonding molecular orbitals in the ground state electronic configuration of the molecule. So this is fundamentally important for the construction of the molecular orbital pictures of the polyenes. Now, in addition to that, one need to observe the signs, algebraic signs of the lobes of the molecular orbital properly. This is easily done by identifying the number of nodes that will be present in the system. The lowest energy molecular orbital has 0 nodes. The next higher molecular orbital will have 1 node. The second molecular orbital will have 1 node, and the third molecular orbital will have 2 nodes. In other words, the nth molecular orbital will have n minus 1 nodes. We will see what this means essentially. The node is essentially a point in a molecular orbital where the probability of finding electron essentially is 0. In other words, the electron density at that particular point is close to 0. Now the nodal points are generally placed at the most symmetric place of the molecular orbital. If we consider the pi 2 molecular orbital of butadiene, take it from me that this is the pi 2 molecular orbital of the butadiene. In a few minutes we will see how we arrive at the pi 2 molecular orbital of butadiene. Now the butadiene pi molecular orbital has 1 node, and that node has to be placed at the most symmetrical point in the molecular picture of the molecule, not at an unsymmetrical point with respect to the node being placed here. In this particular picture, the nodal point is here where there is a change in the algebraic sign passing through the node. In other words, change in the algebraic sign from the gray shaded area with the positive algebraic sign and the empty lobe here with a negative algebraic sign, for example. So it is important to place the node in the most symmetrical point of the molecular orbital in any molecular orbital construction. Now molecular orbitals can be constructed, the pi molecular orbitals of polyenes can be constructed just as easily as the linear combination of atomic orbitals being considered for the construction of molecular orbital pictures of simple molecules. Now here on the left hand side, the ethylene pi molecular orbitals are given. Ethylene has 2 pi electrons. That means it should have 2 molecular orbitals, the pi molecular orbital and the pi star molecular orbital. This is the occupied molecular orbital and this is the empty molecular orbital. This is the bonding molecular orbital and this is the anti-bonding molecular orbital of the ethylene. Now the molecular orbital of butadiene can be easily constructed by the linear combination of the pi molecular orbitals of ethylene. In other words, if you take ethylene molecular orbital and another ethylene molecular orbital, a symmetrical combination of the bonding molecular orbital of ethylene and the bonding molecular of other ethylene essentially gives you 2 molecular orbitals of butadiene, one with a symmetrical combination where all the algebraic signs, in other words with the 0 node of the molecular orbital picture here. Then you have a molecular orbital combination where these 2 molecular orbitals combine to give the butadiene with a node point being present at the center of the molecular orbital here. So the cursor is the nodal point in this particular molecular orbital, whereas this molecular orbital does not possess any kind of a nodal point along the carbon-carbon bond. Then take the 2 antibonding molecular orbital. You can have a symmetrical combination of the antibonding molecular orbital or the antisymmetrical combination of the molecular orbital of these 2 pi star molecular orbitals, in other words the antibonding molecular orbitals of ethylene. Now butadiene is supposed to have 4 molecular orbitals. So we have constructed 4 molecular orbital by the linear combination, symmetric and antisymmetric combination of the bonding molecular orbitals of ethylene, symmetric and antisymmetric combination of the molecular orbitals of the ethylene in the higher energy level, in other words the pi star are the antibonding molecular orbitals of ethylene. This is psi 1, psi 2, psi 3 and psi 4, or you want to call it as pi 1, pi 2, pi 3, pi 4, that is also fine. Now this has 0 nodes, there are no nodal points along the carbon-carbon bond. This has only one node here, in other words there is a change in the algebraic sign or change in the color shading of the lobes of the molecular orbital, so that's the nodal point. At this point the probability density of the electron is close to 0, for example. This has two nodal points. One node point is kept in this carbon-carbon bond, that is carbon 1 and carbon 2 bond. The second node is placed between carbon 3 and carbon 4 bond. So there is one node here, another node here. Now in the case of pi 4 molecular orbital, there are three nodal points. Every one of the carbon-carbon bond has a nodal point. So this is one nodal point, this is another nodal point, and this is a third nodal point. If you follow the cursor movement, you will be able to identify 1, 2 and 3 nodes are being present in the pi 4 molecular orbital of the butadiene. Now this diagram essentially tells you the molecular orbital pictures of the ethylene molecular orbital, the butadiene molecular orbital and 135 hexatriene molecular orbital. Take the example of the 135 hexatriene molecular orbital. The pi 1 is the lowest energy with 0 nodes being present here, and that has 2 electron occupancy, and then the pi 2 with a single node which is placed at the middle of the carbon-carbon bond. In other words, carbon 3 carbon 4 bond, middle portion of the center of the carbon-carbon bond, C3C4 bond is essentially the nodal point, and this is also an occupied molecular orbital with 2 electrons. Then you have one nodal point here, another nodal point here. There are 2 nodes present in the third molecular orbital of the hexatriene unit. In other words, if you go from here, this is a gray shaded area, this is a gray shaded lobe, for example, and then comes an unshaded lobe, so there is a nodal point here. This is again unshaded lobe, there is no nodal point here. This is change in the color of the shading here, so there is a nodal point here. So this has 2 nodal points. This has 3 nodal points, one at this position, one at the center, and one at this position here, which are indicated by the cursor movement here. And then the pi 5 molecular orbital will have 4 nodal points. The 4 nodal points are essentially given by 1, 2, 3 and 4. In other words, there is one nodal point between carbon 1 and 2, another nodal point between 2 and 3. There is a third nodal point between 4 and 5, and the fourth nodal point is between carbon number 5 and 6 in this position here, for example. In the case of pi 6 molecular orbital, there should be 5 nodal points. Every carbon-carbon bond is in the center of every carbon-carbon bond in this molecular orbital is essentially a nodal point with respect to this molecule. You can see here, this is with increasing energy they have placed the molecular orbital. All the filled molecular orbitals have the lowest energy, and the unfilled molecular orbitals have the higher energy in the system. Now the frontier molecular orbitals are the molecular orbitals which are at the frontier of the non-bonded level. This line essentially indicates the non-bonded level. These are bonding levels, and the top ones are anti-bonding levels. So this is a non-bonded level. So this molecular orbital, pi 3 for example, of the hexatriene is the highest occupied molecular orbital, and pi 4 molecular orbital is the lowest unoccupied molecular orbital. So this is the HOMO of the hexatriene, and this is the LUMO of the hexatriene. Similarly, the pi 2 is the HOMO of butadiene, and pi 3 is the LUMO of the butadiene. Here there are only 2 molecular orbitals, one is occupied, the other one is unoccupied. So this will be the HOMO and this will be the LUMO of the ethylene molecular orbital. Now let us try to identify the symmetry elements and symmetry operation. There are 2 symmetry elements that one needs to worry about. One is a mirror symmetry, other one is a rotational axis symmetry. The mirror symmetry is essentially a plane of mirror placed on the molecule in such that the plane bisects the molecule such the mirror reflections are identical with respect to each other. Now let us take the example of trying to identify the mirror symmetry that may or may not be present in the ethylene molecular orbital. This is pi molecular orbital of ethylene. This is a pi star molecular orbital of ethylene. Now when we are considering a symmetry plane, the symmetry plane should bisect the carbon-carbon bond. So this vertical plane is what is the symmetry plane with respect to which we are trying to identify whether this molecular orbital is symmetric or antisymmetric. Now if we place the mirror between these 2 carbon-carbon bond, this passing through the center of the carbon-carbon bond, In other words, the plane is passing through the center of the carbon-carbon bond. The orbital on the left hand side is essentially reflected on the right hand side. In other words, with respect to this mirror symmetry, these molecular orbital reflections are identical. That means they are symmetric with respect to the mirror plane that is placed here. On the other hand, if you take the antibonding molecular orbital of the ethylene, this is not reflected here. In other words, the shaded portion is not reflected by the bisecting mirror. That means this is an antisymmetric molecular orbital with respect to that particular symmetry operation. The symmetry operation being a mirror plane is placed between the carbon-carbon bond, and see whether the left hand side is reflected on the right hand side or not. Here it is not clearly reflected, whereas here this is clearly reflected. So this is symmetric with respect to the sigma, whereas this is antisymmetric with respect to the sigma. So taking ethylene as an example, we are illustrating the mirror symmetry that is present in this pi molecular orbital and the mirror symmetry that is absent in the pi star molecular orbital. So with respect to the mirror symmetry, the pi molecular orbital is symmetric and the pi star molecular orbital is antisymmetric. That is the conclusion we arrive at. What about rotational symmetry? Let us consider a C2 axis of rotation. What is a C2 axis of rotation? It is a 180 degree rotation. Whether it regenerates the original picture or not is what we need to worry about. Here the two shaded lobes are on the top and the two unshaded lobes are on the bottom. If you consider a C2 axis passing through the carbon-carbon bond, perpendicular to the carbon-carbon bond, passing through the center of the carbon-carbon bond, if you make a 180 degree rotation, this is a picture that you will get. Clearly now the shaded portion has become unshaded portion, so the original picture is not generated upon the C2 axis of rotation. Therefore, with respect to the C2 axis of rotation, the pi molecular orbital of ethylene is essentially antisymmetric. On the other hand, if you consider the pi star molecular orbital of ethylene, with respect to the C2 axis of rotation, this is essentially regenerated here. In other words, this lobe here essentially becomes this lobe here by a C2 axis of rotation. So this operation, namely the C2 operation, regenerates the original picture. So with respect to the C2 axis of rotation, the pi star molecular orbital of ethylene is symmetrical with respect to the C2 axis of rotation. So one can identify the symmetry property of a particular molecular orbital either using a sigma plane or using an axis of symmetry. Depending upon the situation, we could either use the sigma plane or C2 axis of symmetry. We'll consider which one of these symmetry operation to be performed at a later stage when we discuss the orbital correlation diagram methodology with an illustrative example. Now in the orbital correlation method, the molecular orbitals corresponding to the bonds being formed and broken are considered during the course of the reaction. In other words, on the left hand side you write the molecular orbitals of all the starting molecular orbital that is undergoing reaction, and in the right hand side you write the molecular orbitals of all the bonds that are being formed during the course of the reaction of the product that is being formed in this. The symmetry properties of each one of the molecular orbital with respect to a symmetry element that is present throughout the course of the reaction is identified. In other words, you identify a symmetry element, it should be present in the starting point, it should be present at the end point, it should also be present in the proposed transition state of that particular transformation that is being considered. So we'll consider illustrative examples in a minute, but try to understand that the symmetry property with respect to the element of symmetry that is being present throughout the course of the reaction or identified is what is important for constructing the molecular orbital symmetry correlation methodology. Then after you construct all the molecular orbital picture and identify the symmetry, you correlate the diagram by matching the symmetry of the molecular orbitals from the starting point to the end point. Symmetrical molecular orbitals of the starting point should match with the symmetrical molecular orbital at the end point. Similarly, the antisymmetrical molecular orbitals of the starting point should match with the antisymmetric molecular orbitals of the end point. This is important. But in doing so, there are certain basic rules that one needs to follow. It is possible that the molecules by themselves are inherently unsymmetrical because of substituents that may be present. If you take a Diels-Alder reaction, essentially the basic framework that is undergoing the Diels-Alder reaction is the 4-carbon framework of the diene, which is this particular one, and the 2-carbon framework of the dienophile, which is this one. The substituents, of course, will have their own effect in terms of accelerating or decelerating the reaction, but it doesn't affect the analysis of the orbital correlation diagram. So one has to strip off all the functional group and take the bare skeleton for the highest inherent symmetry to be considered for the orbital correlation method. You remove all the substituents and take the basic skeleton, which is the most symmetrical with the highest inherent symmetry that is being present in the molecular orbital picture. Now in this case, there are two processes that is taking place with respect to the butadiene molecule. These are electrocyclic reaction. We will come to that a little later. The electrocyclic reaction can either take place by a disrotatory process or by a conrotatory process. I will define what is disrotation and conrotation when you come to the electrocyclic reaction. These two processes have to be considered independently. Although they both give the cyclobutene ring as the product, these two processes are entirely different from the point of view of the symmetry element that is being present in this particular system, which is different from this particular system over here. So we will consider this when we consider the electrocyclic reaction in a detailed manner. For the time being, you must understand that when there are two processes that are inherently possible in a system, the two processes have to be dealt with separately, independently, and not to be combined together, because the symmetry element or the symmetry operator may be very different in this system. The symmetry element that is used for the analysis must bisect the bond that are made and broken during the course of the reaction. If we consider a 2+2 cycloaddition reaction between two ethylene molecules to give a cyclobutene in a suprafacial manner, this vertical plane, mirror plane, essentially bisects the carbon-carbon bibond, both the pi bonds. The horizontal plane essentially bisects the carbon-carbon sigma bond that will be formed during the course of the reaction. So these are the two sigma planes that are present as symmetry elements in this particular system. One symmetry element, which is the vertical plane of symmetry, essentially bisects the pi bonds of the starting material, and the horizontal plane of symmetry essentially, once you consider cyclobutane as the product, that bisects the sigma bonds of the cyclobutane in a horizontal manner. Now if you consider Diels-Alder reaction, Diels-Alder reaction does not have a horizontal plane of symmetry. It has only one vertical plane of symmetry bisecting, passing through the center of the dienophile and the center of the diene, which is this point here and this point here respectively. So this plane essentially bisects the carbon 2, carbon 3 of the butadiene, carbon 1 and carbon 2 of the ethylene molecule in this particular instance, and passes through the center in terms of bisecting the molecule at the mid portion. The symmetry element should be present throughout the course of the reaction. This is what I mentioned earlier also. Through the entire process of starting material going to the product through a transition state. In the transition state also the symmetry element must be present, which will be considered for the orbital correlation, symmetry correlation methodology. Orbitals of the same symmetry do not cross as required by the non-crossing rule. I can give a lot of explanation for this, but I will illustrate this point with the example when we come to the construction of the molecular orbital symmetry correlation methodology. At that time I will explain this properly to you. Now the second methodology, which is the frontier molecular orbital methodology, we consider the highest occupied molecular orbital, which is a filled molecular orbital, the lowest unoccupied molecular orbital, which is the LUMO or the empty molecular orbital. The analysis is based on the interaction between the HOMO of one component and the LUMO of the other component of the interacting system. If you are talking about a Diels-Alder reaction between a diene and dienophile, we will consider the highest occupied molecular orbital interacting of the butadiene interacting with the lowest unoccupied molecular orbital of the ethylene, for example. So this is what I defined earlier also. Let me rephrase it once again. This is the highest occupied molecular orbital of the hexatriene, butadiene and ethylene. This is the lowest unoccupied molecular orbital of the hexatriene, butadiene and ethylene. Essentially the molecular orbital which is at the frontier of the non-bonded level, which is the horizontal line that is shown here. These are anti-bonding levels and these are bonding levels. I mean the pi 1, pi 2, pi 3 are the bonding levels. The pi 4, pi 6 and pi 4, pi 5 and pi 6 are the anti-bonding molecular orbitals of the hexatriene. So this is HOMO and LUMO of the respective systems. If the HOMO-LUMO interaction leads to a bonding type of a situation, then we call that the reaction is allowed. In other words, it is energetically favorable, so it is an allowed process. If the homo-LUMO interaction essentially leads to an anti-bonding kind of an interaction, then we would call it as a forbidden, because the energy of the transition state is going to be much higher than the transition state which goes through the bonding type of an interaction. The homo-LUMO gap is important because the closer the gap, the faster will be the reaction, and that is where the substituents play a very important role in making the homo-LUMO gaps come closer to each other. Substituent effects will be dealt in detail in the case of the Diels-Alder reaction and other reactions. Now the third methodology and the last methodology is to deal with the transition state aromaticity method. In the transition state aromaticity method, the transition state of the pericyclic reaction being a cyclic transition state, the aromaticity of that particular cyclic transition state is being dealt with. In other words, the interacting orbitals of the reactant systems in the transition states are constructed. In other words, when you have a loop of pi electrons reacting, you can have the loop with 4n number of electrons or 4n plus 2 number of electrons, which should consider to be cyclic, aromatic or anti-aromatic as the case may be according to the Huckel molecular orbital theory. Now take the example of a suprafacial migration which is taking place. With respect to this group which is migrating, it is suprafacial. In other words, the bond which was originally bonded here, now it is getting bonded here. This group is migrating from the 1 position to the 3rd position. In doing so, it is undergoing a suprafacial migration. What is suprafacial migration? This orbital essentially which was originally bonded here is now going to get bonded here. In other words, there is a continuous loop of electrons without a nodal point, as opposed to an anti-intrafacial migration. If you look at this picture, it is very clear. Originally this lobe was attached here and now it is migrating to this particular carbon. 1,3 shift is what is taking place in this particular case. So you can see here with respect to the pi framework it is suprafacial, but with respect to this carbon which is migrating it's intrafacial, because originally this is the bonded lobe, whereas now it is happening, the bonding is happening from the opposite side of the molecule, from the other side of the lobe of that particular molecule. So in this particular case, the transition state is cyclic, but it has a nodal point. You can see here there is a change in the coefficient of the molecular orbital of this particular algebraic sign of the coefficient of the molecular orbital. So that is a nodal point. So in other words, this is like a twisted system, twisted loop of pi interacting molecular orbitals here, for example, and this would essentially correspond to a 4 electron system of Mobius type which has an aromatic transition state. Remember, if there is a 4 electron system which is a cyclic system, and if it is a continuously overlapping system like this, then you would call it as a aromatic Huckel anti-aromatic system, whereas if it is a 4n Mobius system, then it will be an aromatic kind of a transition state. It's more clear when you consider the 6 electron system, because it is very similar to the benzene transition state. Benzene molecular orbital picture essentially has these 6 molecular orbitals without any node. They are interacting with each other, and this will be a 4 pi 2 pi suprafacial cycloaddition transition state is represented like this. So this involves 6 electron and it is a Huckel type of overlap. So Huckel type of overlap with a 6 electron would correspond to an aromatic transition state. So if the reaction proceeds with this kind of a transition state, then it would be an allowed process, because an aromatic transition state will always have a lower energy compared to a anti-aromatic transition state. On the other hand, if the 4 plus 2 cycloaddition reaction were to take place in a suprafacial intrafacial manner, with respect to this molecular orbital it is suprafacial, with respect to this molecular orbital it is intrafacial. You can see here there is a nodal point here. In other words, overlap between this orbital and this orbital is what is taking place. So it is a continuous loop with a twist in this position, and the twist is what is responsible for making it as a Mobius strip. A 6 electron system with a continuous overlap of molecular orbitals of this type, which will correspond to a Huckel type, will be aromatic. With a twist it will be a Mobius strip and it will be an anti-aromatic transition state. Now this picture essentially tells you what is a Huckel strip of a continuous loop and what is a Mobius type of a continuous loop. If you look at this loop here, this is all the shaded portion is on the top and it is continuous, and if you have 4n number of electrons in this continuous loop of system, then it would correspond to Huckel anti-aromatic system. If it is a 4n plus 2 kind of an electron, just as in the case of benzene for example, then it would correspond to the aromatic kind of a loop. On the other hand, if you consider this loop, it is continuous up to this point here, and then there is a twist of the loop here, and this is what is known as the Mobius loop here. And the Mobius loop, essentially, if it is a 4n electron system, it would be aromatic, and if it is a 4n plus 2 electron system, it will be anti-aromatic in nature. So Woodward-Hoffmann rules based on the transition state aromaticity can be summarized using this particular slide here. You consider the number of phase inversions that is taking place. In this case, there is no phase inversion, so it is 0. Here there is a phase inversion. You can see here there is a phase inversion at this particular point here. So this will be one phase inversion is happening here. So depending upon whether there is a phase inversion or not, you classify it as a Huckel or the Mobius thing. And if it is Huckel, then it is 4n plus 2 would be an aromatic transition state that will be thermally allowed. If it is a 4n kind of an electron system, it is an anti-aromatic state, it is thermally forbidden. And if it is a Mobius system, 4n will be aromatic, it is thermally allowed, and 4n plus 2 will be anti-aromatic, and thermally it is forbidden. This is essentially talking about the ground state electronic configuration, because we are talking about the thermally allowedness or disallowedness of the process that is being considered. So in this module, what we have seen is essentially a molecular orbital picture construction for simple molecules like hexatriene, butadiene, and ethylene, how to place them, how to identify their symmetry properties of each of the molecular orbitals that are under consideration, and then looked at the various methodologies of analyzing the pericyclic reaction, namely the orbital symmetry correlation methodology, the frontier molecular orbital methodology, and finally the transition state aromaticity methodology. Thank you very much for your kind attention.